to scale up on basis of constant power consumption per unit volume. The scale up based on the constant power per unit volume is done based on the ungassed fluid in both the small scale or the lab scale and the larger scale fermenters. Once the ungassed power requirement at the production scale has been determined, then the gas power requirement can be calculated. Therefore, you have to start with the calculation for the ungassed power requirement. The power over volume, it determines the Reynolds number value. Pi NDI determines the maximum shear stress. When the fluid in the tank is full, the power number will be constant. So the power will be nearly equivalent to N power of 3 di power of 5. So P over V will be nearly equivalent to N power of 3 di power of 2. Therefore, if you have two different fermenter size, then what will happen is the N power of 3 di power of 2 will be equivalent for both of the fermenter. Then you can calculate the diameter of the impeller or the tip speed of the impeller. For the turbulent flow region, the relevant equation is given here. P equals to C rho N power of 3 d power of 5 for turbulent flow. So we can write for small scale, denoted the P with P1, and for large scale, denoted the P with P2. Okay, where the subscript 1 and 2 refer to small and large scales. Scaling up based on the constant power input per volume can be written as P1 over V1 equals to P2 over V2. Alright, based on the ratio. Alright, so you can rearrange the equation into P1 over P2, V1 over V2. Okay. And it can also be substituted with the equation P equals to CP 0 N power of 3 d power of 5 just now. If geometrically similar fermenters are used, the value of geometry dependent constant will be the same for both scales. Thus, it will give you V1 over V2 equals to N power of 3 d power of 5 for 1, N power over N power of 3 d power of 5 for the second fermenter. However, for geometrically similar vessels, okay, you can use the diameter, which is D1 over D2 equals to V1 over V2 power of 1 over 3, meaning that you have to square root by power of 3. Then substitute for D1 over D2 in the equation and you can solve for N2, okay, the tip speed. Alright. Then you can see that the equation for the tip speed, okay, gives the impeller speed, okay, for the large scale, which will consume the same power per unit volume of the small scale. So this equation you can use for scaling up. Transition region. No simple equation can be derived for the transition region relating power consumption in operating variables because the slope of the power curve is variable. In this case, it is necessary to construct the full power curve for scale up purposes. If geometrically similar fermenters are employed in the scaling up, then the power curve will be identical on both scales. The following procedure can be used for scale up in the transition region. The first one is to calculate the value of Reynolds number on the small scale under the defined optimal condition. Then, secondly, find the corresponding value of the power number at small scale, NP. by interpolating the power curve. Okay, power curve here means the graph that we have looked before. Okay, then calculate the power consumption on the small scale for power number. Then you calculate the required power consumption on the large scale. Next, you have to calculate the values of Reynolds number over a range of different impeller speed for the large fermenter. Then find the values of the power number corresponding to the Reynolds number by interpolating the power curve. Then you calculate the power consumption on the large scale at each selected value of impeller speed for the normal power equation, and plot the power consumption against impeller speed on log coordinates for the large fermenter, and find the impeller speed giving the required power consumption on large scale by interpolating the plot. For the viscous or laminar flow region, okay, this region is seldom encountered in scale up because the idea of agitation in the first place was to create turbulence in order to achieve mixing, meaning that we need to have a uniform mixing. So therefore, we have to achieve for the turbulence. However, in certain fermentations involving cells which are very sensitive, they might need this type of flow region. Okay, a very smooth, slow stirring. Okay, such as the mammalian cell culture, gentle stirring use may indeed be the laminar, because of we don't want to damage the cell. Okay, to break the cell, so we need a very slow stirring. Okay, which form a laminar region. If similar approach is used as that for turbulent flow region, but using the equation for viscous laminar flow, then you can use this equation shows here. Okay, equation 6.9 here. It can be shown that for same power per unit volume, meaning the tip speed is equivalent for the fermenter, both fermenter, the small and the larger one. Okay, in summary, okay, the agitation and aeration is very important in the fermentation, and it does affect the mass transfer, the mixing, the production of your fermentation. Okay, therefore, we need to consider all these things: the cell damage, the cost, the foaming, the mixing, the type of mixing itself. Okay, because we need a very good mixing, a very uniform mixing, and in terms of the oxygen, okay, and the carbon dioxide effects. Alright, so it will return all to these all factors here. Okay, we need to consider. Alright, if agitation is higher and aeration, okay, might be higher, okay, you might damage the cell. So you need to know the properties of the cell itself. Alright, if we have a very low aeration and very low agitation, we have the limitation in terms of oxygen, because there is because it affects the mass transfer. Okay, the oxygen transfer in the reactor, you might need a very good oxygen transfer in the reactor in order to grow the cells and have a higher yield of product. Okay, so the agitation and aerations, it does affect all the requirement for the fermentation.